Okay, good. So I am adjusting the deadline for Lab 5. I'm going to make it due on Monday. And that gives everybody basically 2 lab sessions to try to handle those problems in. But today I'm going to focus on Lab 5. I'm going to talk about functions and show how, hopefully convince you of how useful they are. So here is Lab 5. So we have a standard list of learning objectives for this lab. These include how to implement and call functions, what is meant by the term side effect, learn about reference parameters. This is a long list there. I'm not going to just read them off now. And so to try to accomplish those learning objectives, I've given you a set of exercises. And so let's start by looking at the first exercise. We'll do that together in class, and then you can sort of go through that process again by yourself in lab or at home. You don't really need to come to lab to do these if you're more convenient to work at home. But when you do go to do these exercises, even though you've seen me code it up and you write it down in your notes or you watch the video, it's better if you try to recreate the experience without referring to your notes too much. Try to go through that, try to reconstruct that thinking process that I'm trying to convey to you in lecture. Try to go through that thinking process of deriving the solution on your own. And that's really, that's the way you should handle this. So when I give you the assignment, there is an assignment that involves writing functions. And I will not show you in advance how to do the assignment, so you'll have to go through that process on your own for the assignment, and also, of course, in a quiz situation. All right. Now let's look at the first exercise, detecting prime numbers with functions. Now, we did a program in the last lecture on how to decide if or maybe it wasn't in the last lecture, but we have covered it in the previous lab, to write code that decides whether a given number is prime or not prime. And this time we're going to look at how to take our solutions. We're not coming up with a different solution. We're going to have the same essential algorithm, which, by the way, doesn't happen to be very efficient. But just for instructive purposes, we're using this simple algorithm. It's a brute force algorithm. Try to divide every number less than n into n to see if it divides evenly. If you find a value that divides evenly into n that's not 1 or n itself, then you know that n is not prime. So you have to try every number in our approach to decide if n is prime. But there are better approaches than that. So we looked at code for this already. Does anybody remember which exercise of Lab 3 that was in? Was it exercise 2? Yeah. 1, exercise 1, okay. So I'm going to copy, what I'm going to do is I'm going to show you how to reorganize your solution for exercise 1 so that you place your code into a function. And the function name is going to be isPrime. And I'm also going to show you how to use the assert statement in order to write test code that will test. So instead of manually, visually inspecting the results of your program, you're going to write code that will programmatically test the correctness of the code. All right, so here we go. This is the folder name. Last time I talked about the screen utility, and I'm going to use screen again for those who want to learn how to do it. You can listen to these comments. if I may already have a screen session running in the system. I can check that by doing screen -R to resume that already running instance of screen, but it's not there, so I know that I don't have it running. So I'll start up an instance of screen. Actually, well, yeah. Let's go into the folder. I'm going to make a directory, lab051, cd into there, and I'll copy from lab 4 exercise 1 that code, because that has our solution to this prime number determination problem already. So it's just a matter of reorganizing. Whoop. I don't have that? Oh, I never did it. I only did it in lab, didn't I? Okay. Well, all right, so we have to write it up from scratch. That's all right. I'll take any problem. I know there's going to be a loop. I'll just leave that in there. All right, that's good. Got our first step done. Got our development environment set up. Got an editor open with a program in it. I've got another window where I can quickly do a compilation and a test. I got my starter code compiling and running. So what the let's suppose, just before we dive into the problem, I want to talk about what a function is. Let's do something like this. Let's print I. We're in a loop. We're in a loop. And say we want to do something over and over again. Maybe it's just to print I. So I ranges from 0 to 99. And let's print that inside of the loop. So there it is. And maybe this thing here does a lot more. Maybe it does more things. Maybe it prints I squared. And then after printing I squared, it goes to the next line. Say it does more. I and I squared. All right. But now the main, maybe this block of code gets more complex. Maybe there's a loop within it. And so what we want to do is I'm going to split the code up into separate sort of levels of responsibility. This code is responsible to sort of iterate through I. That's the loop, the outer code, the main function. And then the code that's on the inside, say, takes each individual I and does something with it. And that could involve another loop, for instance. Well, actually, in our case, it is. In our case, we're going to... Well, no, that's not true. hold on that. That's not our case. What we can do is take this sort of block of code here and place it above main and declare a function, and I'll call it print, say print I. And this function does something for us. So now it's a little easier for us to look at this the contents of the main function. We just have a loop that goes from that takes an I, ranges it from 0 to 99, and then whatever I, for each I that we get, we invoke a function called print. We pass the I to that function. It's a function. I used to have the code in here. I did that detailed work at this point, but now I want you to do that detailed work for me. Here's the I, print it squared. And then when you return back to me, then I'm going to increment I and then call you again. So this function here represents a block of code. And you can, by using the function name like this, passing in some arguments, 0 or more arguments, you can tell the compiler that you want machine instructions generated so that that block of code executes. And then after that block of code executes, return back to this point. So branch into the print function, execute the logic there, which are these two lines, and then return back to me where I called you. This is called calling a function. See? I'm calling a function here. I'm invoking a function. I'm using it as a command. The compiler reads this line and says, oh, I need to generate machine instructions that branch to another block of machine instructions that does something and then returns back to this point. This is called calling a function. When you call a function, you have the function name, a parenthesis, opening parenthesis, 0 or more arguments that are separated by commas if you need them. So you could have ij, that would be, of course this won't compile because the print function is not declared as taking 2 arguments. The print function is only declared as taking 1 argument. So, but I'm just showing that you could declare it as taking 2 arguments. It would look like this. There's a function that takes 2 arguments. Okay, so let's just go ahead and do that. And rather than the square of I, let's do I times j. And we'll print I, then we'll print j, then we'll print the product of I and j, and then a new line. But j is not defined, so we have to define j. All right, let's do this. So you have a loop within a loop. Oops. Maybe we won't go to 100. We'll go to 20. So now we have a loop. I ranges from 0 to 20. J ranges from 0 to I, or I minus 1. And then we say for each of these pairs, I and j, print something about them. You see how we can think now about, we can leave some of those details out, and we can read this code more clearly. Let I range from 0 to 19, and for each value of I, let j range from 0 to what I is, and then print something about them. And then let's just leave aside what it is we're going to print about them. So we can focus on the structure of the logic in a simpler way. Because we're setting aside the details of what we're going to print about those pair of i's and j's. What we're focusing on is how do we write code that iterates through all the pairs of integers that I'm interested in. That's what I'm focusing on now. Once we sort of mentally get that understood and coded, then what we can do is shift our attention and say, oh, okay, for each pair I and j that we have, let's take a look at the details here. Let's look at what we're actually printing. See the benefit? Because this is unnecessary. We don't have to use functions. Functions are optional. Functions are not needed. Internally, the machine, everything that you can code up on a computer with functions, you can code up without functions. So its only purpose the purpose is not to make things work technically. It's to make the code easier to write and easier to understand. That is the purpose of a function. Well, let's see if this works. Looks good. See, in the left-hand column is I. You can see that I is ranging from 0 to 19. This is where it transitioned from 18 to 19. And j ranges from 1 to I minus 1. You can see it's when I hits 19, j starts at 0, and for I being 19, we check each value of j all the way up to 19 minus 1. And then we print their product. Just to make that more clear, let's do this. This is easier to look at. So I starts at 1. Oh, the inner loop never runs, yeah. Thank you very much. When I is 0 and j is not less than I, j equals I. Very good, thank you. Let's suppose we want to see, we want 0 times 0. Uh-oh. Oh, I thought an infinite loop. So 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2, 3, 0, 3, 1, 3, 2, 3, 3. So that's how that works. That's kind of a common sort of iteration that you see a lot, actually. All right, let's get on. Now, there's some details here. Remember, the purpose of functions is to make your code more readable and maintainable and writable. Maybe it's your working style to say write main first, and then after you get that top level job done, then you're going to define the print function. Let's suppose you do this. That's more readable to you. That's the purpose of functions. So let's suppose this is your style. This is what makes it understandable to you. This will not compile. The print was not declared in this scope. Do you see this? There's an error. Print was not declared in this scope.
See, when the compiler processes the source code, remember the job here, we're not running the program here. I didn't run, when I did this, I didn't run the program. I ran the compiler. I told the compiler, read the file and produce an executable that I can then load into RAM and run. So when we ran the compiler, what the compiler does is it goes through one line at a time of the source code and tries to basically understand it. And so when it gets to here, it says this is a sharp sign or a hash mark. And I know what that is. I'm a compiler. Then it should be followed by what's called a pre-processing directive. Okay, so I read the sharp sign. That means there's a pre-processing directive coming up. I didn't read it yet. All I read was the sharp sign. So now I'm going to read the I. Oh, okay. And then an N, then a C, then an L, then a U, then a D, then an E, and then a space. So, oh, space. That's a delimiter. I'm going to review what I just did. I just read in the word include following the sharp sign. Oh, that's the include pre-processing directive. Okay, that makes sense to me. But if we had something like this, when the compiler hit the space, it would say include DT. That's, I don't know what that is. That is not a pre-processing directive that I'm aware of. This is an error. This syntax error. I don't understand this token. So what we're doing is we're parsing, we're breaking up these characters into what are called tokens. It doesn't understand this token, but it understands this token. So when it reads that, it then continues, and then, basically that's how it thinks. That's how you can sort of trace out what's going on with the compiler. And let's go back to the error message. It says, it gives us a line. It also gives us the character position in the line. So line 12 and column position 23. Counting starts at 0, I think. Print was not declared in this scope. So that means the token print appears in the source code in line 12. And when the compiler pulls that token out of the stream of characters, it says, I don't know what this token means. I'm going to print an error message and terminate. Line 23. That's line 23. Oh, sorry, line 12. There, right there. So that's line 12, and the compiler reaches here and it's going to parse this token, print, and says, I don't know what that is. That's because we delayed the definition of print till after we define main. So the compiler is processing the file sequentially. And that's kind of a fact that I'm trying to convey to you, is that in computing, there is a lot of sequential sort of execution, and that you need to get your mind into sequential mode to understand how things work. You don't always think in a sequential way, because holistic, I'm going to tell you the difference between these concepts. You've got holistic understanding, holistic thinking, and then you have sequential thinking. Holistic understanding or thinking would be to look at the whole file in one glance and extract meaning out of it and understand it and see something and that it's meaningful to you. That's kind of a holistic thinking. But to understand how it operates step by step, you need to think more like the computer, which is to read the first character, and then what do I do? Read the second character, and then what do I do? So it processes these instructions in a sequential way. So to analyze a problem, you need to sort of understand what is happening in that sequential process. So when the compiler is analyzing these characters, it gets to print, and it says print is undefined. Because it's doing it sequentially. It's not like us. It's not like a human. A human would say, hey, print's defined right down there. What do you mean print's not defined? There it is. But the computer doesn't look ahead. It just does one thing after another. By the way, the sequential execution it's not the whole story. You've got branching and looping. And so that's makes it's a little bit of an oversimplification just to think everything is done in a sequential manner. But it is one step after another, even though you... Okay, so the two solutions there is, well, let's bring the print function up above main and put it back where it was. Or we could say, wait, that's not my style. And what I want to do is tell the compiler that main is a function. And print. This is called a forward declaration of print. Now I'm telling the compiler that, okay, when the compiler reaches this line, it says void and then print. And then at a certain point, it's going to say, oh, this is a function. This is a function. Now functions, just like main, see main, a function, the definition of the function starts with the opening brace. Print, the definition print starts with the opening brace. But here, the compiler reads this and says, well, I've got a function, I got a return value, I've got a function name, I've got my opening parenthesis, I've got my first argument, which is an int I, second argument, int j, closing parenthesis, that's the end of the argument list, and then, where's my opening brace? You didn't give me an opening brace. Oh, you don't want to define the function. You just want to tell me that this function exists, and you'll give me the definition later on. This is called a forward declaration. So we have no opening brace here. We just have a semicolon right away. So now when the compiler gets to this line here, it says, oh, I've got a function called print, which I know the programmer has promised to provide me a definition for. He just told me that it's coming. He didn't give it to me yet, but I know it's coming, so I'm going to accept this token as a name of a function called print. And sure enough, when we get to this point, print, the same sort of function signature, we call that a function signature, the return value, the function name, and the argument list, that's the same as this function up here, the function signature up here. But this time, we're using that opening brace and providing the definition. All right, let's see if that works. And we're just going for compilation here. We're not talking about execution. That works. Okay. So that's called a forward declaration. Let's get back to the problem here. And the problem is to detect prime numbers. So we want a function, and I'm just going to copy that right in there. This is a function called isPrime that returns a Boolean value. If the number passed into it, n, is prime, then the function returns a true. If n is not prime, the function returns false. So this initial token in the function declaration, in the function signature, this first token is what's called the data type of the return value. When a function runs, you branch into the code that runs the function, and then when the function returns back, you can use that function where you call it from in an assignment statement. And you get the return value from the function as the right-hand side of that assignment statement. Let me show you. So see, print, look at the difference. Print, the return value for print is void. That means it doesn't return anything. It just does something that returns back to you. But is prime is declared as returning bool. Let's get rid of this. I'm going to get rid of this whole thing. So we call the idea here is that the function contains the code that checks to see if n is prime or not, the value passed into it, and it returns true or false. And that return value is assigned to another variable or used in an expression directly. And so we can have code that's conditioned on that return value. Oops. So here's what that would look like. So let's suppose we want to know what, so we call the function is prime and pass in the value 7. We don't have it defined yet. We just have it declared here. And actually, so it will compile. This won't compile because it doesn't have a return statement. Let's just say that every value passed into it is prime for now. Will return true. So that's a temporary implementation. That's called a stub, by the way. That's a stub. It's a function that just compiles and runs, but it doesn't do what it's supposed to do yet. So we call is prime, pass into 7. It has that evaluates to a value, which is of type true, so of type bool, which is true or false. We store the value in result. Result is a variable declared as type bool. And then if result is true, then we're going to print is prime. Otherwise, we're going to print is not prime. Well, that didn't work very well. It looks like, it should look like this. Let's do it like this. Let's have a variable set called n set to 7, and we'll say n is prime. N is not prime. Now I'll put my new line in here. I just don't need to use that n line. This is essentially equivalent to inserting this control sequence into your string. This is a backslash. That's called an escape character. it tells the compiler that not to interpret the following character for what it is, but as a representation of something else. So in that case, it's not going to print an N. It's going to say, oh, you want a new line here, not an N. Let's call it an escape sequence. It still didn't print it. Why doesn't it print? What did I do wrong? N is 7. Did I not compile? Oh, maybe I didn't save. Really slow. Really slow. There it is. 7 is prime. All right. Now let's get the code in here that actually determines whether N is prime or not. So we start with, you know, we're going to start with 2. And we're going to look at 2 all the way up through to n minus 1 and test to see if I divides into n. So if n mod I is 0, then it's false. It's not prime. We found a factor that's not 1 or n itself. Does that work? Yeah, that works good. And if we go through the loop and we don't find any factor between 2 and n minus 1, then we know that it must be, that n must be prime. That's our algorithm for determining primeness. Can everybody remember that algorithm? N is prime if we try every number between 2 and n minus 1. If every single number that we try in that range does not evenly divide into n, then n is prime. And this is how you express it as an algorithm in the C++ language, which looks very similar to all the other languages. All right. So now, this should print n is prime. Or 7 is prime, rather. Let's try 8. I think this should print, you know, if we pass in 8, see, we can either say, oh, I remember we finished the implementation of the is prime function. I don't have to mentally check it. Or if we forgot or we're not sure, then we might want to mentally step through the code again, verify that if I pass in 8, it will in fact return false. Well, it will, because like when we set I to 2, we take n mod 2, we'll get 0, and so we'll end up returning false. So is prime, oh, this is not right. This should be n, sorry. So is prime with 8 will return false here. So this if condition is false, so that means we're going to print 8 is not prime. Now, see this if condition here. It looks at the thing that's the characters, the symbols that are in between the opening and closing parentheses of an if statement. Those evaluate to true or false. So that's a Boolean expression. This is a bit redundant. I mean, result is either true or false. So we don't need to do result equals true here. We just do if result. Because result will be either true or false. So if result is true, then we're going to print is prime. You see how that's a little unnecessary to do that. So this is a more compact code. But we can take that another step. We don't really need to store result as an intermediate value. We can use the call to is prime directly in this if statement, in the condition of the if statement. We can use that directly. We don't need this line. We don't need to create an extra variable called result. We can just call is prime, pass in our n, and the result is the return value is going to be true or false. And we can use true or false in the condition for the if statement. All right, now the problem. So we've done this. We've implemented is prime. It does what we need it to do. Now let's use this assert statement. It's called a macro. Actually, it looks like a function. But it's processed at that pre-compilation step, but I'm not going to go into those details. So let's change our main function so that it becomes a test function. Here's my first test case. I want to call is prime with the value 2. And is prime should return false. I mean, sorry, true. Should return true to pass in 2 because 2 is prime. And so when assert gets true, it just is quiet. But if the argument to assert evaluates to false, then assert will terminate the program and display an error message. So you're asserting, like, I assert that it's sunny outside today. So nobody complains, because I said a true statement. If I assert, it is raining right now. Right, that's an error. So you have an error there. So assert, in our programming, that's how we use assert, essentially. Now to use it, we don't need this C standard line. This we use for the C time function, so we don't need that. We need a header to use assert called not assert, C assert. That's it. We need C assert as a header to include And that header includes a definition of this assert function, or actually it's a macro, but I'm not going to get into that. I'll see if this works. Oh, and you know, this is just going to silently execute without saying anything. So we get nothing. So what I'm going to do is just add some statement here. I'm going to say that all tests passed. There's all tests passed. And let's assert another one. Let's assert that that is prime returns true for 3. And is prime returns false for 4. So we need to negate that, because is prime will return false for 4. So we need to negate that to make it true, to pass through the assert, the assertion. Is prime should return true for 2. Is prime should return true for 3. Is prime should return false for 4. But false will crash the assertion. So we need to convert that false into a true. So we use the not operator. It's called a Boolean operator. The negation operator, not the not operator. Well, you could say it like that, but I think the correct term is negation operator. All tests pass. You know, let's suppose we had a bug here. Let's suppose instead of starting at 2, we started at 3. Well, I got a better one. Let's suppose we started at 1 instead of 3. So this is a different algorithm. Wait, make sure I saved that. Let's see what happens. Oh. A.out main.cpp gives us the line 20. In int main, it gives us the name of the function. It says assertion is prime 2 failed, aborted. So that's how assertions work. So we know, oh, we got a mistake. I mean, is prime 2, you know, that should be true. But, you know, we're asserting that that's true. The line 20, I'm going to go to line 20. Is prime 2, this returned false. Now we can do the debugging. Our test has failed. So we go through here and say, well, what happens when we pass in a 2? Well, we set I to 1. And we do n mod 1. Is n even? What's the remainder when you take... Wait a minute. Is that right? 2 mod 1 has no remainder. Yes, it's 2. 2 divided by 1 is 2 with no remainder. So the remainder is 0. So returning false. I'm trying to think and talk at the same time. Sometimes it's hard to do. Okay, so we corrected the program. There we go. We got it. We fixed the bug. Well, let's make sure that we have all the bugs out of there. Let's just test. And here's two values that are important to test for this algorithm in my experience. 9 and 27. These are not prime. And maybe something like, what's a big prime number? 97? Is that a big? We tried 57 last time, didn't we? Was 57? It was non-prime, right? We found a divisor. Was it 19 times 3? Actually, we're going backwards. We're using our code to test our test code, so it shouldn't be that way. But we're going to do it that way anyway. So we're writing test code based on our code that we're trying to test. So if we believe 97 is prime, then this assertion will be true. 100 is not prime. We got it. Okay. That's it. This is what you should end up having at the end of your session with this particular problem. All right. I did that on purpose. Oh, I didn't want to add a dot out on purpose. I made that mistake. I'm going to do SVN remove minus force. There we go. All right, that's committed. So we have a few minutes left. Let's take a look at the next problem. What's that? 1. Let's see what the next problem is. Oh, listing prime numbers with functions. So we're going to use the isPrime function now to generate a list of prime numbers. We're gonna have the user enter in a number, say like 100. We'll run the program, and the program will list all the prime numbers less than or equal to 100. And we did this problem already in an earlier lab. And you ended up having to write a loop within a loop. But by using the isPrime function, we don't have to have a nested loop. Nested loops are difficult to understand and analyze. So if we replace the inner loop with the isPrime function, we just have a single loop. And let me show that to you. I'm going to copy over our isPrime function, our code with the isPrime function. Now this function is already tested. let's read in a number n that we prompt the user to enter. And then for all numbers between 2 and n, I don't remember, I said I didn't read it carefully. Is it less than or equal to, or just or less than? I don't say inclusive or exclusive.
It's between the 2 and the number entered by the user.
Okay, between. Is that inclusive or exclusive? Sounds exclusive to you? Between 2, that means we'd want to start with 3 then, right? Oops. Maybe I should I should change that. Let me be more specific. I was thinking to be inclusive. So I'm going to change that to inclusive. How about if I do it like this? I'll use the adverb. Inclusively. Is that the right way to do it? Oops. Huh? All right. So let's make this back to a 2. And this is exclusive. I mean inclusive, sorry. So if, let's use our isPrime function, our handy function. If I is prime, then we got one. I'm going to put a space there so that we don't, get them all together. And we don't print this, but I'll print a new line at the very end. Maybe I should do something else. Prime numbers from 2 to n are, oops, need a space after the n before the word r, and also I need to have this new line in there, otherwise that won't look right. Enter a number, 100. That looks good. So the prime numbers from 2 to 100 are, and here they are. They look prime. That's it. This is an example where we have this. We need a loop to determine primeness using our algorithm. And we need another loop to iterate between 2 and the number entered. Rather than having a loop within a loop, which we did in the previous lab, we have a single loop. And we branch, execution branches to a function called isPrime to do that additional work for us, the detailed work. Save my work. Commit. The next exercise, listing random colors with functions. So all of these exercises are revisions to the previous lab. In the previous lab, we wrote code that would generate, I think it was 100 random color values in hex notation. So now we want to reorganize the code so that generation of a random color string is performed in a function. Use functions to remove any nested loops, loops within loops that are in your code. Let's try this. Is it 4? It's lab 4, right? So let's just copy that code in here. Is it 4.4? I'm going to copy over top of what I just did, just like that. It doesn't warn you. You know, at the command line here, it didn't warn me. Are you sure you want to overwrite an existing file? It didn't give me that. It just overwrote it. All right. I'm going to do this quickly because it's a long session to listen to me talk about coding, I think, right? Anyway, here is the function, and it's big. And let's just do some software engineering here. We're going to chop this up. This I'm going to put the main is going to be down here. I'm going to get all this 1, 2, 3, 4, 5. I'm going to get. I'm going to copy 6 lines, or 6 YY. I copied 6 lines. I'm going to put it down on the bottom here. This is the beginning of our new main function. So when main runs, we're going to seed the random number generator. We're going to go, we'll do 10 instead of 100. We'll do 100 later. And then we're going to call this function. There's 2 ways of doing it. Let's do it like this. Let's do cout. So random color. Or I guess we can do it like this. Different ways of doing this. Let's create that function called random color. There's different ways. It depends on what we want to do in the long run. So this is a void function. Oh no, I'm sorry. It returns a string. And the function generates the random number. The other way we could do it is, see the loop, we put the loop on the outside. The other way to do it is to pass in a random value. There's that. And here, this is where the function printed this RGB string. But now what we're going to do is we're not going to print it in here, we're going to return it. Now I need to fix this up. My indentations are too much. There's a lot to do manually, but I'm doing it anyway. I just want to make sure that you see how concerned I am about cleanliness and what is this? So we have a function called random color. It returns a string. To play it safe, some compilers will have string defined already, others won't. Let's include the string header. Random color returns a string. Here we create the string, define a string here, set it to null. We did this already. All right? We're not going to review that code. We have that engineered piece of software already done. We're just moving things around. We're not reviewing the algorithm to do this. We're just repackaging to make the system easier to maintain and understand. So generate, we know we need to do this, seed the random number generator. We only do that once. We don't do it over and over again. And then here's our loop we call random color. It returns our random string. We print it. Let's take a look. Oh, it builds. We're lucky. Looks good. Try it again. It's a different string. We got it. Oh, there it is. Is there any questions? Final thing I'm going to do is commit my work. And that's it. Okay, so I've delayed these assignments till next Monday, or this lab until next Monday. So you have time in over two lab sessions to do this. Please get a head start on assignment 2. You need to get